Hello everyone, and welcome to lesson 28 of the Save My STEM Physics channel. We're still in the mechanics section, and we're going to be doing something that I thought I'd already done, but clearly haven't. We're going to be doing Newton's laws. So obviously, the king of classical mechanics, of classical physics even, and he postulated his three laws, um, and they govern the mechanics course for Year 12 Physics in the AQA A-level course, um, and also at GCSE. So you will be familiar with them, but I'm just obviously here to make sure that you're brushing up with it and also maybe delving into things a little bit deeper or seeing things in different forms. So let's get started. Newton's first law is I'm just going to put a big first there. An object at rest stays at rest unless a resultant force acts on it. A moving object moves at a constant velocity, which you may want to expand means constant speed and direction, unless a resultant force so that is at length, right? So an object at rest stays at rest, and a moving object stays at constant velocity unless a resultant force acts on it. This can be shortened into a system is at dynamic equilibrium unless a resultant force acts on it. So dynamic equilibrium means that it can be moving with a constant velocity or stationary. Dynamic equilibrium may even mean that it is rotating. Um, a rotating object can still have no resultant force on it. That's something that you'll find on the further mechanics section of the course. Um, and if it wasn't rotating, it'd be at static equilibrium, but again, this is conversation for another day. So you can just shorten it to a system is at dynamic equilibrium unless a resultant force acts on it. But how does a resultant force change the velocity of a system or of an object? And that's what the second law says. So, the second law is basically always referred to simply as F equals ma. So the force applied is equal to or is a product of the mass of the object and its acceleration. Right? Simple enough. Another form that you may see this in, and this is actually the form that Newton made himself, is that F is equal to delta mv over delta t. It is the rate of change of momentum. But how are these two equations the same? So, if we take acceleration, acceleration is in meters per second squared, right? So the dimensions of acceleration are meters per second squared. It is also, so acceleration equals delta v by delta t. the rate of change of velocity. So that must mean F equals m multiplied by delta v by delta t. And we can regroup this into F equals delta mv by delta t, right? And simple as that. You may know already, or you may not know yet, that mv equals p, which is momentum, lowercase p, and therefore the force applied is equal to the rate of change of momentum. In other words, if you put a momentum, if you put a graph of momentum against time, the gradient of that graph will be the force applied. So that's the initial form that Newton intended, and one stipulation with F equals ma that I forget about, frankly, I forget about it quite a lot, is that for F equals ma to be true, m must be constant. There, there are situations where technically it could be the velocity that is constant and the mass could be changing, but as a general rule of thumb, it will never be asked like that. It will always be the velocity that is changing and the mass that must be constant. If you, say, have a question about a rocket ship, uh, it will be losing mass as it travels upwards because it will be burning fuel. That fuel will be released, and therefore the rocket loses mass. So when a question asks you about it, they may tell you to ignore the lost mass or assume that it has a constant mass, and then it may ask you, what's the issue with this model? Well, it's losing mass, so F equals ma is not applicable. Finally, the third law, you may the way I always used to remember it at GCSE, and this was stupid because it doesn't give you any marks, was Hamilton. Hamilton says, well, not Hamilton, but in the show they say every action has an equal opposite reaction. Simple as. And that is the gist of it. But unfortunately, that doesn't get you any marks. You have to be really technical. If object A, and obviously I'll put this in quotations because you need to sub in object A, so say like a ball and a wall. If object A exerts a force on object B, again, going to put that in quotes, then object B will exert a force on object A which is equal in magnitude but opposite in direction. And that is Newton's third law. Every action has an equal opposite reaction, except you need to be more clear rather than concise. And those are Newton's three laws. You may, if you do further maths, hear about Newton's law of restitution, which is like it's not officially his fourth law, but it is something that is regarded as one of his laws. Um, but this is as far as it goes for A-level physics, and this is the terminology or the way that you'll see it. So thank you very much for watching, and I'll see you all in the next one. Bye.